All right. Okay. Let me share my screen. Okay. So can you see the screen as well?
Yes, I can see the screen.
All right. Okay. So last time we talked about energies, right? And we were discussing gravitational potential energy. These were what we were discussing was mechanical energies, right? So gravitational, the potential energy and kinetic energy falls under that category. And so the types of potential energies that we were discussing was gravitational potential energy. And today, let's start with the another type of potential energy, that is the elastic potential energy. This is also a what do you call that? A mechanical potential energy, right? So today we'll start elastic potential energy. Before we proceed, is there any question from anyone regarding the previous lecture?
No questions for me.
Anyone else? Is there any question regarding the last lecture?
No.
All right. Okay. So if there are no questions, then we'll proceed. Let's quickly talk about the elastic potential energy. In any system that you can stretch, you can store this type of energy, an elastic potential energy, right? So we know potential energy is an energy that you can store in a system, that is stored inside the system by doing something to that system, right? So for example, gravitational potential energy was energy stored in a system. If you raise a system to some height, right, then this would possess gravitational potential energy. What about elastic potential energy? Any system that I can stretch can store this type of energy, right? So any stretchable system will have elastic potential energy. By stretchable, I also mean, expanding or compressing, right? So both of these fall under this category: expand or compress, right? So for example, a spring, you can imagine that if you have a spring, I can compress this spring like in this way, and so it will become something like this. I can even expand this spring, so then it will become something like this, right? By moving the ends in this direction. So if this was an original spring, this is the compressed spring, or compressing the original spring. When I compress it, now it has some potential energy, and that's the elastic potential energy. Or when I expand the spring, then it also stores some potential energy, elastic potential energy. So now let's write down a mathematical expression for such type of a system. So for example, the force on this type of a system, which is the restoring force, will have to, okay, so I'll have to quickly give you an idea of what a restoring force is. So for example, suppose that a spring is attached to this wall and there is some block of some mass m. Now this spring will have a constant called k. This constant for a spring depends on the geometry and the materialistic nature of the spring. So what is the spring made up of? How thick is the spring, right? And all those properties, right? We'll not get into those, but this K depends on those properties. It's a constant. Now, if I were to move this mass, pull this in this direction, then the spring would expand, right? It would stretch, it would expand, and the mass would move over here. Now, suppose that I have pulled this mass in this direction and now I release it. What will happen? It will come back here to its original position. First, it will come back to its original position. Then it will move a bit more in this direction. Then it will come back again in its original position, and then it will move here. So it will essentially start oscillating. The case that we have discussed before as well for a pendulum. So it will start oscillating. When I pulled it to the right, there's a force that's pulling it back to the left, which that force is known as the restoring force. It's restoring the mass in its initial position, right? In the mean position. And this force for a spring depends on how much I have moved it, displaced it from its original position. That displacement is suppose X. Now this force depends on that X. The more I move it to the right, displace it to the right, the more force there will be to pull it back to the left, right? You can do an experiment, take a spring if you have a spring or any system of, or even a rubber band. The more you stretch the rubber band, with more force it will come back to its initial position. That's why if you take a rubber band and you hit it on your leg, for example, if you displace the rubber bands very slightly, it will not hurt as much. But if I displace the rubber band a lot, then it will hurt your leg, right? So the reason it hurts more is because there is more force when you displace it more. So that's why it depends on X. That dependence is clear to everyone. Why would the force depend on the displacement?
Yes, it's clear.
All right. So when I join these two to make an equation, there comes a constant with this, and that constant is the spring constant, right? So that's the expression for force. Now, my goal was to find the elastic potential energy. Now, because of this force, which is pulling the mass back into its original position, there will be some, it will come back to its initial position by converting the potential energy into the kinetic energy, right? So when I displace it, it has stored some potential energy, and now it's coming back to its initial position by converting the potential energy into some velocity, that is the kinetic energy. So I need to find what potential energy is stored in the system. I can do that by using this force, because I know that any type of energy is related to work done, right? And I need energy to do work. And work done is simply force times the displacement, X, right? So this is work done. And this work done is done by the potential energy, the elastic potential energy. So this is the elastic potential energy. So what is force? Force is Kx, and then I have another x, right? So this becomes Kx squared. Now there is a factor that we have to include, and that factor comes by some doing an experiment and then checking, plotting a graph, and then finding the area under that graph. And there comes a constant of 1/2. And this constant comes from the fact that when you plot a graph, right? So the graph looks like this. If this is f, this is x, then the graph looks something like this. And if I find the area under this graph, it will be the area under this curve, right? So it would be half f times x. So it would be half f is kx, and then you have another x, so this becomes kx squared. So the elastic potential energy can be calculated by half kx squared, where K is the constant associated to the spring, or if it's a rubber band, then it's a constant associated to the nature and material of that rubber band. And X is the displacement, how much I have displaced in order to expand or compress the rubber band or the spring, right? So is this clear? Is the elastic potential energy clear?
Yes, clear.
All right. Clear for everyone? Shall I proceed forward to kinetic energy?
Yes, sir.
Everyone is okay with elastic potential energy? Is there any questions?
Yes,
Any?
okay.
All right. Okay. So Taha or Muiz are always active. I would like the rest of the class to also actively participate, so that we can make things a bit more interesting, right? Okay. Anyways, we'll move on to the next topic of kinetic energy, right? So I've used the word kinetic energy very often. We have talked about it before as well, in previous chapters as well. Uh, its definition is still the same. Everything is still the same. We'll just see how can we compute this kinetic energy, right? So kinetic energy is energy that is associated to the motion of particles, right? So anything that is moving or that can move, it will move because it will move because of the kinetic energy, or it will possess kinetic energy because it's moving, right? So for example, I have any object, any ball. If I kick this ball, it will start moving, right, with some velocity v. So the the force that I have used to kick the ball, I have done some work in kicking this ball, and that work that I did was converted into this velocity, meaning it was converted into some other energy that is associated to velocity, and that energy is the kinetic energy. Now imagine this. Why I want to do that is because I want to see what does it depend on, right? The kinetic energy. Imagine that the ball was massive. Then you would need to kick it more hard to get it going, right? The bigger the ball is, then you would have to kick it more hard, so that it can start moving. So that means that this energy, which is associated to moving, would have to be more if the mass is more, right? Does everyone agree with that?
Yes, I agree.
Right?
Yes, sir.
Okay. So uh, the kinetic energy, normally we write it as K dot E. There's another term abbreviation that's just using T. Sometimes I might switch in between, so I'm just telling you, but I'll try to stick with K dot E, because I think you're more familiar with this thing. So Ke is the kinetic energy, and it depends on the mass. The more the mass, the more kinetic energy I need to get the ball going. And it also, obviously, we have already defined kinetic energy in terms of velocity. It is associated to velocity. It depends on velocity as well. It just turns out that it depends uh, on velocity more than kinetic energy. Now, so that means if I increase the velocity by doubling it, then the kinetic energy would become 4 times its initial value, right? And using these things, I can write down the formula for kinetic energy as half mv squared. Any system that is in motion or moving will possess kinetic energy that you can find by this expression. So the motion then completely depends on the mass of the system, and obviously the velocity, how fast it's moving, right? So that's kinetic energy, right? So for example, if I say that imagine that you see a car and that car is moving, and the mass of the car, suppose it's 1000 kilograms, and you see the speedometer of the car, where while you're just sitting in the car, you look at the speedometer and it says it's going at 100 uh, kilometers per hour. Then sitting in the car, just for fun, I can compute its kinetic energy. The car would be having a kinetic energy of half times 1000 kilograms times 100 kilometers per hour. And so this becomes 250s are this, and then you can do the math, and the kinetic energy that you would get from here would be in terms of kilograms, kilometers per hour, right? I cannot write this in joules just yet. It is energy. It has to be in joules. But for that, I need to get rid of this kilometer per hour in term meters per second. So I can do that easily by replacing 1 hour by how many seconds are there in 1 hour? 3600, right? And how many in I can replace this k by 1000, so this will become 1000 meters, and then you can do the unit conversion, and I'm sure that you can uh, do these conversions, and when you do them, the answer is in joules. The kinetic energy, the SI unit for kinetic energy is joules, right? The SI unit for any type of energy is joules. So that's kinetic energy. Now I'm going to quickly talk about one of the most important principles in physics, which is the conservation of energy. Okay, in very simple terms, conservation of energy just says that I cannot get rid of energy entirely. Whatever the form of energy is, it's going to remain there. It might be converted into other forms, but the energy overall cannot just disappear into nothing, right? So you can think of an example. There are millions of examples that you can think of. One of them could be, suppose that I have this container, and I have a lot of gas molecules in this container, right? Now, suppose they're just sitting around. The gas molecules are, you can just imagine, although it will not be always like this, that they're stationary, but just imagine for a moment that they are sitting still, doing nothing. How can I get them going? One thing is I can heat the container, right, with some flame. When I
Yes.
do that, right? So I'm providing some energy, and this is heat energy, thermal energy, or and that energy goes into the container. Of course, now you have to think more. You can think more and more deeply. You can just say that one thing you can say is that heat goes into these molecules. But if you think even more deeper, it also goes into these walls of the container. Now, the walls of the container are also made up of atoms, right? So there are also electrons, molecules in the walls of the container itself. These electrons will also gain some energy that comes from this heat of the flame, and eventually that's how they'll transfer this energy into these molecules inside the containers. And then the molecules that are inside the containers that I've drawn as circles, they'll start slowly moving. So this heat energy has been converted into kinetic energy. And what will happen is that these molecules, they start moving, they will eventually start hitting each other. And there's a transfer of energy happening over there as well. It might also happen that these molecules hit the walls of the container. And so, because the walls of the container are made up of electrons, they will transfer some of their energy into the containers, the electrons or atoms of the container, and lose energy and start slowing down. And that energy has not been lost. It did not just vanish into nothing. That energy went into the walls of the container. But the walls of the container are so strongly held because it's a solid. The molecules are so strongly, closely packed that this energy that I transfer from these loose molecules, the molecules that are just moving around, they're loosely packed, is not strong enough to break the walls of the container. But obviously, we know that if I heat it so much, so high, at very, very, very high temperatures, then the container will start breaking. And it starts breaking because I have given it so much energy that the walls of the container, the atoms, they could no longer take all that energy uh, to still stay, in contact. But now they have broken apart simply because of the fact that I have given them more energy than they could possibly endure, right? And so that's why things, when you heat up some things, they you can observe some cracks and them breaking. And if the temperature is so high compared to the nature of the material that they're made up of. So I'm going very deep into things right now, but the main idea is that the energy is not lost. Energy can never be just lost into nothingness, right? So conservation of energy, uh, I like to say it as energy can never be lost into nothingness. Other things that you'll hear is that energy can neither be created nor destroyed. It can be only converted into one form of the or the other, right? So it's in two parts. One is no creation or destruction of energy. And the second most important part is that uh, if obviously if it cannot be created nor be destroyed, what can be done with energy? You want to know that, and that's what the second statement is telling you. It can only be converted, right? So nature has given you some energy in the universe, and you can just play around with that energy, but it will never be lost into nothing, right? So that's conservation of energy. That's the principle of conservation of energy. Is there any question up until this point?
No questions.
No questions. All right. Okay. So I'll give you an example that you'll be more familiar with, and it has to do with potential and kinetic energy. So let's go on to this page. Uh, Suppose a situation where you're hammering a nail into a wood. Just give me a second. All right. Okay. So suppose that here I have a wooden piece. There is a nail on this wooden piece, and you'll have to completely ignore my drawing. I don't know how to draw a hammer, but just assume that this is a hammer. right? And I'm slamming this hammer to basically push this nail inside this board, wooden board, right? What would, how, just think about this. If I just put the hammer on top of this nail, will that be, will the nail just go in, or
And no, the will
what?
not go in.
It will not go in. Or what do I have to do to make this nail go in? What do I
You
do with
have
the hammer
to apply force on top of the nail.
on top of the nail, right? So I can do that if I raise this hammer. I'm raising this hammer to some height. So suppose again I'll have to draw the hammer. So I don't like drawing. Uh, so just imagine that this is the same hammer. I'll raise it, and then again I'll bring it down without stopping it and hit the nail, and I'll see that the nail went in. But the nail was not going in when I would just keep the hammer on top of it. Or even if I just raise it slightly and hit it, I would not see much of a difference. But then it occurs to me, okay, let me just try raising it a bit more, and then boom, uh, the, the nail went inside. It's no magic. What happened is, if I raised the hammer, I have raised it to some height, h, and I have given it some potential energy. And then that potential energy, when I brought it back down, was converted into kinetic energy. So what's happening is the gravitational potential energy converted to kinetic energy, right? Because when the hammer goes down, it moves down with some velocity. So the energy conversion is from gravitational to kinetic, and that kinetic energy does work. And that work done is obviously done because when the hammer hits, there's some force applied, and the nail moves some distance x into the board. And so that's what's work done, right? If you apply a force and it moves some distance, then work is done. So the work was done by the kinetic energy, but indirectly because I got that kinetic energy from the gravitational potential energy. So what happened is that the hammer had some kinetic energy when I raised it to some height, and then I hit the hammer down. So hammer was falling down, and that kinetic energy converted into the gravitational potential energy converted into kinetic energy, and that kinetic energy did work by applying some force. The hammer applied some force on the nail, and the nail moved into the board. Obviously, when that happens, if you hit the nail and you just, if you want to, you can check that the nail would slightly feel warmer, right? And not only that, but when you hit the nail, you will also hear some sound, right? So the entire gravitational potential energy or kinetic energy was not used to just do that work. It was also, some of it was also used as sound energy. Some of it was also used as heat energy, right? So that's conservation of energy, right? So the energy was never lost anywhere, but it was used in all of these things, right? So any question from this thing?
No questions. I understand.
Oh, all right. Okay, so if this is like this, if you understand all of these things right now, if things are like this, then how come when, I'm saying that energy can never be lost, I've been saying that so many times. If you throw a ball, suppose if you throw a ball Let me try to draw it like this. If I throw a ball like this on a ground, it will what will happen is, suppose I'm throwing it from some height, right? This is the ground, and the height is h. So just so that it has some potential energy, mg h. Yeah, I know what the path of the ball looks something like this. It will go down, it will hit the ground, and then it will again rise, but it will not rise as much, right? And it will again hit the ground, and then again it will rise, but not as much, and hit the ground, and then it will again rise but not as much and hit the ground, and eventually very it will become so small, and then it might stop. The ball might come to a rest over here. So this is a very interesting curve, where if I said that energy cannot be, lost into nothingness, then I would expect that when it hits the ground for the first time, it should come back exactly at the same height with which it hit the ground, because the energy was it shouldn't be lost into nothingness.
it
Then what
it
happens
is
when
converted
anyone
it is converted into other forms of energy like sound, because the ball hits the ground, and also the ground
right,
also absorbs some energy.
right,
It's
all right,
converted.
okay. So it's converted. So the very straightforward answer is yes, that it is converted into other forms of energy. And as you said, those forms are, of course, you'll when it hits the ground, you'll hear some sound. So sound energy. When it hits the ground also gains some energy, and that's, if you think about it more deeply, that's very interesting actually, because every time you throw something on the ground is left shaking more than it was before, right? So if you hit something, maybe with a hammer, with a ball or anything, you will see, you can feel it. If you touch that thing, it will slightly feel a bit warmer, right? And the reason for that is that the molecules or the atoms are moving, they gain energy, they start moving, and that moving of molecules is what we call hot, right? Warm. So the energy is transferred into the ground. The energy is also lost because this experiment was not done in vacuum. There is air around you. And so a ball must have hit these small, tiny air particles, air molecules, and had given transferred some of its energy into all of these air molecules as well. And so the air is also slightly warmer around this ball. So the air that is around this ball will be also slightly warmer. And these things are very interesting. If you think about these things very deeply, you can do an experiment like this also. It's a simple experiment throwing a ball, and you can observe all these things. And it turns out that, these things are as they are, as we're talking about them. That's the truth, right? So this was more or less the conservation of energy. And this principle is very, very important in physics, and it is applied everywhere in the universe, right? Except for one thing. And I think how much time is left?
2 minutes.
2 minutes. So I think we'll talk slightly about that, and then we'll finish this topic of energy. And in the next class, we'll talk about power and efficiency, and the chapter will be finished, right? And hopefully, we'll start the next chapter as well in the next class. So, conservation of energy is a principle that physicists, we often say that this is a very fundamental principle of physics, and it really is. right? It really is. But how many of you are familiar with the idea that the universe is not stationary, that the universe is expanding?
Yes.
Everyone agrees with that. At least you
Yes,
must
sir.
have heard it somewhere, one way or the other, right? The
Yes.
universe is expanding, right? So if the universe is expanding, can you think about this principle of the energy conservation of energy? I said that in the universe we have some amount of energy, and that energy is what we can play around with, right? But we cannot create it or destroy it.
Less than
What?
1 minute.
Yeah. So, but it turns out that the universe is expanding. If the universe is expanding, then the space where all these particles can be, right? All the particles, or planets, or anything for that matter, can be. If the space is expanding, then these particles have more area to cover. They can cover more area. And so how can I say, if the space is expanding, how can I say that the energy is conserved? Energy has to be not conserved now, because if this there is